Okay, thank you. Let me go ahead and reshare the screen so that people can see what we're looking at. There we are. Thank you, everybody, for joining us for our penultimate colloquium of the semester, actually. It's shocking that we're so close to the end. But today, we are very excited to welcome one of our honors students, Charles Gross, and Dr. Greg Hogan, who's Division Chair of Natural Sciences and Mathematics here at A&M Texarkana. And today they're going to be talking about a project they've been working on, which I'll simply read it to you with the intentionality that I know what it means. Can hydrogen bonded metal organic frameworks mimic clay functionality? Why, I know the answer, but for all the rest of the people in the audience, please enlighten us, gentlemen. So we should have some time for questions at the end. Thank you. Yeah, get after it.
Thank you, Dr. Nakash. And so, like he said, you don't have to switch it just. Oh. Okay. So my student work, Charles Gross, is going to give you, once we get to that point, I'm going to go through the introductory of a lot of the material in the beginning, and Charles will illustrate a lot of the work that he has done within our research lab from last spring and a little bit over the summertime, kind of exhibiting what he's done. And we're actually in manuscript preparation. So his work that he's done and that we're showing here is hopefully about to be published shortly after submission. Okay? Yeah. Okay, good. Thank you. All right. So in our intro, what we're going to look at is it's a very similar to the approach that we always take within our lab itself to illustrate that there's multiple ways in chemistry to make things. All right. And that's our big key, is the fact that we're focused in on the development of chemicals, molecules, and in our case, going to be frameworks. How can we develop those? And you see, we have a wide variety of things at our disposal, from basic organic chemistry. We chose a specific chemical reaction, but again, it could be any organic process. All right, here, like a Heck reaction that you see, we can take a molecule called styrene and react it with a palladium catalyst and iodobenzene, and we can chemically couple those two together. Woo. Okay. Or we can choose a basic inorganic synthesis where we use the actual chemical reaction across the metal itself. In this case, what's called an oxidative addition, that we can take an iridium compound, take a basic diatomic hydrogen, and add the hydrogen molecule across iridium. All right, so it's just showing you that there's many different directionalities that you can take. All right, and then with our last case, we have what's called a supramolecular synthesis. So this one's not truly an exact chemical reaction. It's actually allowing for intermolecular attraction to occur, and we allow molecules to come together, right? Because that's going to be our general approach that we're going to look at. As myself as an inorganic chemist, we're dealing with metal organic frameworks. So we're going to see this relationship of inorganic synthesis, but it's also called metal organic. So we're going to see the relationship of organic chemistry as well. And we're going to put it all together with a little bit of supramolecular synthesis. Okay? Because you've got to probably click the screen.
Click on the screen, then you can move it.
So yeah, just touch it.
There.
Okay. All right, so this is with respect to supramolecular synthesis. So again, these are all known weak interactions, quote, quote, weak. But we placed in a few at the very top just to kind of show you the top of the regime that we could possibly have. So ion-ion interactions, so we're talking about like basic salts, sodium chloride, so cation, anion, has a range of 100 to 350 kilojoules per mole with respect to interactions. And as you can see, it goes down in energy through the list and hit. So our first example just showing you is what's called an ion dipole interaction between what's the molecule called a potassium 18 crown 6. So potassium is the ion that's in the center. And the 18 crown 6 is what's called the crown ether molecule. And nomenclature-wise, 18 means there's 18 total atoms, and there's 6 oxygen atoms that make up, in essence, a crowned structure. Okay? And our second one that we are going to emphasize based on our title, hydrogen bonding. All right, so out of the true intermolecular attractions that we have, it has one of the highest energies at the top end. So it has the potential to be very strong with respect to intermolecular attractions, but in some cases it can be as often pretty low. So you see this range of 4 to 120 kilojoules per mole of energy. And then again, so I have to click the screen. So again, as you can see that interaction right there, the little dotted lines, those are our hydrogen bonds that are keeping these benzoic acid molecules in close proximity to one another. All right, now, types of hosting molecules. So this is where we're going to now draw our comparison for the organic side of things to the inorganic side of what we can see that currently exists. So as you see, with respect to organic frameworks, we have here a little crystal structure that's being generated by a hydrogen bonded framework that is 100% organic in nature, of what's formed through what's called a guanidinium disulfonate. So the guanidinium is this little guy right here, this blue. The disulfonate is kind of like, looks like a pillar, right? It's holding up that little layer, right? And inside you can see it has this molecule called p-xylene. These guys are all right there. All right, and then on the other side, we see what's called a coordination polymer, which is an inorganic species. But the majority in literature, we don't see many hydrogen bonded based inorganic frameworks. Energetically, they typically form through what's called a coordination polymer. So it's all just direct bonding between these yellow centers. Those are the metal, in that case, iron. And so we see the identification of just standard covalent bonds, okay, which is good, but we don't have the direct correlation of a hydrogen bonded species, right? And we're interested in the weaker interactions because these have been studied extensively, okay? Hydrogen bonding, not as much. Right, so that's where we want to take into this concept and go into, right, and start looking at our host molecule, and we want to draw it back to, because of the same functionality of clays, right? Because that was in the title, right? Can our hydrogen bonded metal organic frameworks mimic clay functionality? And so with clays, we can see that this is a general structure, molecular formation of a true clay, and that we have the aluminum silicates, and inside of the layer, we have this hydrophilic region because clays love water, right? It rains, right? The ground soaks up all that water, right? Typically inside of a clay. And then as time persists, if we have wonderful heat, which we're not going to have anytime soon, eventually you'll see all those cracks in the ground, right? Because our clay is going to absorb water. The layer, this region of space between, will actually increase because it's forcing more water molecules inside. And then once it's opened and heat comes, these water molecules escape. But we don't see much of a change until, somebody will do something to our ground, right? Step on it, run on it, and then you see all of it decay. Or you just simply witness the large cracks through crevices that are generated from the loss of water, right? So the functionality that we're looking at is that ability of our layer to swell. We want the ability of changing the distance between the layer components, okay? Now, with respect to that, so now focusing directly on the inorganic system, so we're drawing our comparisons. We have the pure covalent system. So this is a wonderful little organization from a gentleman out of College Station itself, Dr. Clearfield, that again, it's metal that's all bonded through covalent systems. Okay, still no identification of a weak interaction. Everybody's going for just this big one because it's the easiest thing to do. We can mix things together, they'll covalently interact. Wow, okay, that's fine. But as you can see on this example, we can have a non-covalent system, which is through the use of intermolecular attractions, i.e. hydrogen bonding, that we can contain our framework, and it's hard to see, but there's these little bitty turquoise dots. Those are all our hydrogen bonds. And it's keeping these frameworks together because now we can see a distinct layer, and then we have our interlayer distance, our interlayer region that we can place small molecules inside. Okay, and this is a previous work. This is from my group itself. So this is something we haven't published. It's just a random structure that I couldn't fit it into anything of a manuscript. So c'est la vie. Now, once we have our host frameworks, right, we want to look at the clay functionality. So how can we put molecules in and remove them inside? Well, with clays itself, we have that ability for molecules to simply just transport in and out, right? There's no interaction with the framework itself, so molecules, water can go in, give a little heat, they can go right out, back and forth, okay? The one issue with these other types of systems, like what we have generated, is that it forms what's called a close-packed system. So meaning to form the framework, it has to have a good organization of that framework. The problem with that is we're not allowed with all of the extra space like a clay would have. So we have to use this to our advantage and try to develop our frameworks and undergo the insertion before we form our framework. So we're in essence going to place molecules and then allow the framework to come around it, and we can hold our molecule inside. So it's a little bit different, but on the grand scheme, it's going to be the exact same process, because we will see, not in this work, but it's been done, that our frameworks are reversible. We have the ability, just like clay, put something in, remove it, in, out, back and forth. I was bored one day in lab about 10 years ago or so. And I was like, yeah, what the heck, let's try it. I stuck some molecule inside, did an analysis, it was there, heat it, removed it, checked it to verify it was gone. And I was like, okay, let's do it again. Let's do it again. Do it again. Up to 10 times. Framework maintained its complete integrity from removing and insertion. Clays, we may not get that ability. Okay, because then we've got to start worrying about other things going inside of our clay itself, which will kind of degrade the exact clay material. Okay. All right, so how do we analyze all this? This is where all the fun stuff comes in, right? So this is all the analytical instrumentation. So all the fancy instrument that we are now finally starting to develop here on campus. Jesus. Okay. But the first one, the most important, we undergo X-ray analysis. Okay, so we will use at our benefit the technique of growing crystals and analyzing crystals because of their exact functionality that they exist. Okay, the first one, a single crystal X-ray diffractometer. Diffraction, right? That's what you're going to see extensively what we have, okay? Because that is our finite determination of everything. Because if we grow a crystal, it's analyzed, the structure's determined, there's no disputing it. That's the structure. It's finite to a T, okay? Everything else might give some sort of ambiguity within its determination. But the single crystal is always correct. It's kind of like Charles in class, he's always right. Okay. Okay, and then we have a second technique in the same thing of X-ray diffraction. It's called powder X-ray. Okay, let me backtrack. So single crystal, Charles, how do we handle single crystal samples?
We send it out to College Station?
Yeah, so we grow them, and we send them to College Station. Okay, because they're fortunate enough to have two of these between $500,000 and $750,000 instruments. Okay, we don't have those. I won't ever have those here. Okay, no, not the one. It's been a long time since I saw one, so I would need to hire somebody to do it. But the second one, this powder X-ray diffraction, we will actually have one of these instruments on campus in January. So they purchased over in summertime, and it was hoping it to be in, but red tape and such. That's all I'm gonna say. Won't be here till January yet, and then we will be able to have a mechanism to continue to analyze our samples. Because where we can't grow good crystals, we can take crystalline material and still analyze it and get good enough data that we can use. Okay. The thermal analysis, we have one of these instruments on campus now, the thermal gravimetric analyzer, the TGA. Again, purchased, I think it was last year or so. I think so. So this one's been on campus for about a year, give or take. Another instrument, this is why they're fancy, is because they cost so dang much. All right, that powder diffractometer, it's about $90K. The TGA that we got that we have already is about $45,000. So again, that's the the basic model, right? There's no upgrades to that, no 22-inch rims or anything. It's just standard, okay? And the rest that we have, chromatography, the NMR, nuclear magnetic resonance, infrared spectroscopy, these are great techniques, but they have limitations. Okay, limitations in the sense that NMR is great if you're doing pure organic, but if it's in an inorganic system, we generate a lot of interference with our metal and the magnet that's inside of the NMR. Okay, anybody's ever had an MRI done? It's the same technique, but they don't tell you that it's the MRI. So they don't want to let you know that it's a nuclear generated system. So they leave the N off on purpose. Okay. Now, IR spectroscopy, we'll see again, this is a basic organic technique that we have a lot of overlap based on the spectrums that we would generate within our molecule. There's just a lot of the same type of frequencies that will be generated, and there's no determination specifically for what we have. Okay. All right. So almost done at the beginning. All right. So a unit cell, this is where we apply our crystallography. So this is going to be the premise behind X-ray analysis. All cubic substances, anything that grows in a crystalline form, has what we call a unit cell. It's our way of measuring the X, Y, and Z directionality of our molecules. And so we typically will draw kind of this cubic-ish system so that we can identify that A and B is going to identify what we call, that's our plane of our layer. So when we show all the pictures, you have a layer, interlayer. Okay, the AB distance will generate the actual layer of our substance itself. And the C is that distance between our layers, right? The swelling portion of our clay, right? So that's the one key aspect of what we're going to focus on, is looking at that interlayer distance and what can happen to it. Are we expanding or are we not? If we get some expansion, then we know we have clay functionality, right? We can expand the interlayer distance. And that's what we're going to look at, and it's all backed by what's called Bragg's Law, father-son combination that won a Nobel Prize way back in the early 1900s. And it still exists perfectly with respect to our unit cell. And so what you will see later, you can flip it, what we will show shortly, and that Charles will go through, is that with our structures, when we generate the entire framework, what we're doing is we're taking unit cells and we're stacking them side by side, top and bottom. That we're just taking one repeating entity and we can expand it three-dimensionally. But we're not going to look at it 3D, we'll just only look at it 2D because we have a 2D screen. Okay, and we can't see that third dimension coming out. So, but just pay note that when we look at it, you will see unit cells. So Charles will remind you of the unit cell, and then you will see when we combine all of those unit cells. All right, so basic thermal analysis. Okay, so the concept with the TGA itself is that what we're looking at, it's a fancy furnace with a microbalance. So we will know our mass of our substance, and as we heat it, we will see weight losses occur, and we can correlate those weight losses to things inside of our framework. So as you can see, just a crude example, a host with 2 guests, we can see as we increase temperature, right, we can lose a guest, and so we'll see a weight loss. And then we could lose that second guest, and it just simply down to the host. And at some point, the host can just simply decompose, vaporize, wherever the heck it may do. Okay? All right, so we're getting close to Charles. All right, so again, what can we expect if we place molecules inside of our frameworks? The 2 biggest things. We would see extra weight, right, in the form of the molecule we've added. So we will see extra weight loss that we will determine by our TGA. And then also we can confirm layer expansion through our X-ray analysis. Right, so that's our 2 big things we're going to look at. So that's what we're going to show is X-ray data and TGA data. All right.
This is all me?
You can. Remember, this is the intro version of it, not the specific.
The introvert?
Yeah.
Okay. Oh dear. Okay, so what we do here is we are forming the AB layer. So this whole thing right here, so we take the metal PDCA, react it with. So did I say that wrong?
You could just call it, it's 4-methylbenzolamine, but you could just focus it, just call it an amine.
Yeah, okay. The metal PDCA plus the amine in a solution of methanol and water, and you create this hydrogen bonded metal framework right here. So the AB layer.
But
Oops.
that's the important factor. The important concept of all this is we do all this for one reason, because it can generate a simple, stable framework. And this is going to be repeatable no matter what we do. Okay, that's the key concept, is that it's simple and it's stable. Now tell us what you did, Charles.
So what I did in lab was I took copper sulfate and I reacted it with picolinic acid in a solution of methanol and water to create the unit cell of the framework. Let's see, and that's the component of the AB plane.
Yeah, it's perfectly fine.
Okay.
So again, as you can see, an actual structure of just the molecule itself that we will use. So this is the metal organic, right? Because we take the inorganic copper with a pure organic of, like Charles called it, picolinic acid, 2,4-pyridine dicarboxylic acid, to generate that nice, wonderful metal compound. Okay, now what did you do next?
Then next, we took the created metal compound, reacted it with a very specific amine and methanol and water, and then we decided to, after creating that that framework right there, we included a gas molecule for insertion, bromobenzene. So what?
We tried.
We tried, yes.
Okay, so now this is the part where, like we were saying, so this is technically now generating the unit cell of our framework. Because now what we have the metal dicarboxylic acid species with two amine molecules. And remember from the picture, the framework, and it had a dangling molecule in between. All right, so now what happens, Charles, when you put them together?
Like all this together right here?
Yeah.
Okay. No result of insertion of the gas molecule, but the framework is constructed.
So hopefully you see now what we've done. This is the organization of unit cells. Because we have our metal pyridine dicarboxylic acid, and this is the amine molecule. And as you can see, there's that picturesque view of the two that we just saw. So here, nothing happened, okay? Remember, in science, no results can be good results as well, right? It's just not always clear cut. Yes, it's going to work every single time. All right, so that's what we use, and we learn from it. And so we modify.
Okay. And the results here showed there's no divot at the top because there was no insertion, like gas molecule to leave, right?
Right. So this is the PPA of the thermal analysis of the empty framework. So as you can see in the very early on, and this is a derivative of it. So we're looking at the change with respect to the temperature as we increase. And there's just nothing going on very early. We see a slight inflection, which is going to be the loss of our water molecule that's on side of our connected to our metal. But after that, after 200 degrees, this is just our framework starting to decompose. So that's what we're going to key on, is what's happening early on within the first 100, 150 degrees.
Okay. Then we try the same metal PDCA again with an amine, and we used 1-hexanol as the gas molecule. Okay.
You're leading.
And the molecule was able to be inserted into the structure as highlighted by these circles. Oops.
This interview was going to be a lot quicker. So hopefully,
Oops, I'm sorry.
it's all right. So as you can see within all of these frameworks, we have included the 1-hexanol molecule inside of our framework. We can see it via our crystal structure. We see the intact framework, our interlayer, and it worked. Okay, which is good, right? Like I told you, we learned from something that didn't work. So we changed our approach and went to something a little bit smaller, a little narrower, that can probably wiggle its way inside of our framework. And a key is we have a non-coordinative guest insertion. Coordinated would just meant that this molecule would have been bonded to our metal, but in this case, nothing. Okay, no interactions, just molecule free inside of that framework.
Okay, and there's a divot at the top, which means as the heat increases, the gas molecule starts to leave the structure, and then the structure eventually just starts to decompose as you increase the temperature even more.
So nice, good example. Before 100 degrees, there goes that hexanol molecule leaving our framework.
Then we did the same metal PDCA again with the amine, and we used 1-pentanol as an insertion gas molecule, indicated by this.
So key is that we found the system that works, right? We found a molecular system that works nice. We've got these little chained alcohol molecules, and they squeezed in nicely inside of our framework, continuous hydrogen bonded pattern. So we didn't lose any integrity of our framework. We're inserting molecules just like we expected to. Okay.
Okay, same thing again, but this time with 4-chlorobenzyl alcohol. And right here.
So a little bit different. Okay, framework is still maintained. The biggest key point is what we tried earlier when we got nothing inside was we used the bromine, which was extremely large. And this time, so we cut it back and went smaller with chlorine. And as you can see by this lime green coloration, that's a chlorine atom. And the alcohol of our benzyl alcohol is showing it is bonded there. But one thing that we have to pay attention to of how we label this is called a disordered chlorobenzyl alcohol. So what happens with X-ray structures is we can have a disorder, which means that molecule, once my crystallographer does his work, he puts the molecule in one orientation. So meaning the chlorine could be pointing up and the OH of the alcohol pointing down is one perspective. And you can also have it in the opposite direction. So what you're seeing is an overlap of those two possibilities. And so we can't show them completely connected. So that's why the best determination, we see it in this perspective. Okay, but we know it's in, and that's the biggest key component for this point.
Okay. Sorry, I thought you were, okay.
Okay.
And then have a divot at the top again, the gas molecule is leaving, and as temperature increases more, the structure starts to degrade.
Yeah, so we just left off the derivative, but you would see that again, you can identify a huge loss early on because of the size of benzyl alcohol or chlorobenzyl alcohol is extremely large. But again, pattern of everything exactly the same, that we're generating the loss and degradation of our framework well after 220 degrees Celsius.
Okay. And the same thing again, but with a benzyl alcohol as a gas molecule. Okay.
And so interesting with this one is the fact, so we removed the chlorine off of the molecule, so it's now just pure benzyl alcohol. But the one out of all of our examples, this molecule is actually interacting back with the framework. All the rest has just been a freestanding molecule with no interaction. Now it's generating some interaction with the framework itself. So it's contributing back to the hydrogen bonded framework. Okay, which is again interesting. And again, we still see the same level of disorder. Again, the same picturesque that we're overlapping both of our structures on top of one another. So it makes it look like it's like a dihydroxy species, but it's not. It's still just the one. Okay.
Okay.
All right, so this is the comparative analysis of all these frameworks. So looking at the relative unit cell parameters, the A, B, and the C. So the one thing to pay attention to is that, so we have our empty framework, the hexanol, pentanol, 4-chlorobenzyl alcohol. So we're going right down in that general facet. So as you can see, it went from 17.8 to 21 to 21. And then again, we saw a slight contraction with the chlorobenzene, and then again, it opens back up with benzyl alcohol. So are we expanding our framework as we put molecules in? Yeah. So in some cases, we're seeing greater expansion than we typically would. In literature, a lot of the organic frameworks, when they place molecules in, they may get a half of an angstrom greater increase. And we're seeing upwards to almost 3.5 angstroms of space. And so angstrom is that A with the circle on top. That's a 10 to the negative 10 meter. So we're talking nearly three units larger in space of increase. All right, and then we're also seeing a wonderful correlation between the lightness of our molecules and the determination of the framework. So if you really paid attention when we placed the alkyl, or the two alkyl alcohols, the hexanol and the pentanol, the framework was a little bit more wider. Okay, and then the last two with the chlorobenzyl alcohol and benzyl alcohol, they were more close packed, right? They were more together. And we're seeing that with respect to the relative determination, but overall, right? So we see the wider of our layer with the 16 and 17 angstroms, and then again, the more narrow with the almost 6 angstroms of space. Okay, so yes, we are seeing this interlayer distance increase, our C parameter. So yay, right? We can identify clay functionality. The true test is going to be what we will do in the future with it. So if you're curious, those are some wonderful pictures of crystals that we grow. All right, a lot of times what we're doing is we will place all of our components together and then we generate all of these little crystals and we just keep them in a vial. We just ship them off in that direction. The crystallographer we'll find the best source and analyze those crystals. We don't give them back though, so once we submit, they're gone. I know it's a shame. I wish you would send them back. I'd have to pay for return shipping, I guess. Too cheap for that. Okay, so, but yeah, so if anybody's interested in this, yeah, this is our biggest thing. We grow crystals. And when we change for different metals, we will see the color change with these crystals as well that will tailor back to the actual metal itself. Okay.
Yeah, ready.
Do you want to go ahead?
Oh, no, I thought
Oh, I was gonna say, so, what was that?
you were still under the slides.
Oh, no.
Okay. Okay.
So our conclusions is simply is, our synthesis that we've talked about, that was one of the other components, right? We want to make sure we can generate through hydrogen bonding reliable synthesis, right? Every single process that Charles did, and some of the other guys you'll see in a little bit with our pictures, right? They have all been reproducible. If we mix this thing that Charles called that metal PDCA with an amine, we put them together, we can specifically identify what kind of framework we're going to generate. May change a little bit because some of my original thoughts have fluctuated based off of what we have in these results versus what we presented last time. Last time we generated what were called bilayers. Now here we have 0 bilayer structures. Okay, so can throw a little monkey wrench in there with us. And again, we can identify our C parameter, an increase in value that tells us we do have clay functionality. Okay, we're not going to see extremely large increases in the distance because at some point it becomes a thermodynamic kind of system. If they're not close enough, then our framework would just go to kaput. Okay. And then some current things we're doing in the future, right? So we're looking at these exact same results like what Charles is doing, but now we're going to change the metal complex. So Charles investigated copper. We're looking at, so what's some other ones we're doing?
Nickel, cobalt.
Nickel, cobalt, and
Iron. Is iron one?
iron, zinc.
Zinc, okay.
So we're looking at other metal complexes to see, can we continue the same framework? The answer is yes. Because nickel has been crystallizing fantastically over the summertime and this early fall that I have some structures of those as well. So, yeah, so working great. And then we can also look at creating of other frameworks, some mixed amines. So can we change out the 2 amine molecules? We've seen they've always been the same. So can we have that phenethyl on top and then something else on the bottom? Don't know. Be interesting to find out. Mixing metal, can we have 2 different metals inside of our framework? And pillar structures, which I think you did some pillars this summer, right?
I think so.
So then those are also going to be probably our next topic of discussion at our next conference. Is that we have generated some pillar frameworks with wonderful crystal structures already. I think we have 3 good ones. And so all of this information, Charles was supposed to present at a conference with a poster in October at the American Chemical Society. So all of this, his abstract, everything was submitted. We were good to go. And then we had to have some faculty hiring things come across and we had to cancel our trip. So I know who, one more Chuck.
Okay.
Thanks a lot. I know. And so these are all the guys that did all the groundwork that started the majority of this. A couple, some of you may recognize, somebody you may see right in the middle that you may know. So our first graduate, our second or third, so I can't even remember. Charles is going to be our next most recent one in the spring, graduating with his degree in chemistry and hopefully going to University of Colorado. If Coach Prime's still there, he might join the football team too, you never know.
Yeah, sure.
That is.
And that's it, so.
All right.
We'll say thank you.
have time for a question or two, or
did I do?
depending on how long.
What do you need him to do? Anything over here, Craig?
I'll come up and take care of this. I'll field the questions from the front. Any questions from the audience before I ask my, you can go out here, Charles, it's fine.
Okay.
Very cool. Not all at once.
So with your organic metal framework, are you looking to have a specific niche build for like, something you're trying to do with it? Or was it just to see, if we could get this to come about?
Yes, that's, take that off with thinking, I was trying to keep it to 30 slides. The idea with all the metal organic framework, they have 4 major categories they like to look into: separations, storage, which hits both of these. So the idea that these metal frameworks can hold specific molecules for transportation purposes, because a lot of these organic molecules that we place inside of our framework are very flammable. And one interesting thing that I've actually tested, that we can place somebody that's a very flammable molecule like hydrazine, it's a component of jet fuel, can store it inside of these frameworks. It can heat the framework itself. The flammability of the substance it's gone. So we actually can store very stably flammable materials without the flammability worry of those molecules. So yeah, and that's actually what we're focusing on, is the storage aspect. That I've been looking at some wonderful grants from the DOE based on all this, so we may start trying to tie back into there. But yes, storage was number one. And a lot of it was getting the ground up of just getting these frameworks established. But next will be separations with respect to it, because these frameworks can selectively remove one molecule from another. So a lot of DNA purification uses benzene, but they don't want benzene in the DNA. So this molecule can selectively remove it without touching anything else. So that's more future work.
Cool. Yeah, that was gonna be my question on the applications. And I remembered the transportation one, I think, from last time. I think that's really, really cool. All right, any other questions for Charles or Dr. Hogan? Otherwise, we will free them.
So if you're storing it, will it still function the same? Like whatever you're storing inside of it?
So will the molecule still exhibit everything the same with the framework?
Yeah.
So
Yeah, so
Like the molecule.
Substance, flammable, and then it can still be.
yeah, so as long as the molecule stays inside of the framework itself, it's protected. But once it comes out, it's going to exhibit standard behavior. So like what we've done before in the past was take something like acetone, fingernail polish remover. Very flammable.
Yes, it is.
Place it inside of a frame and heat it, allow it to evacuate inside of a closed tube, and allow a little bit to squeak out and light it on fire. It will maintain its normal chemical properties after, once it's released from the framework itself. So, yeah, so we do not destroy the actual, we do not destroy the molecule in any way. It's just we're going to hold it. And depending on what the temperature of which we're, heating the thing to, we can protect it.
So is this at like such a small level, like it could never be like an actual product? Like if like you could make actual nail polish removal not flammable?
Yeah, can you scale it? How big can you scale it up?
Yeah, the scaling up itself can happen. The only problem with scaling up a lot of these framework systems is to get chemical properties out of them becomes very difficult. Because once you take it from the molecular side and try to take it to more macro scale, the transition between the two kind of loses a little bit its luster. But on the small scale side, yes, it can. But macro, we haven't looked into. That'll be if we're going to try to send this to like research and development. I think it's mine. Okay.
It's Charles.
So
He's in demand.
yes, potentially later. But at this point in time, we're still on the small side.
So you're not gonna have refrigerated truck that can transport a large.
And but see, that's gonna be
Not
the
yet.
difference thing is with that transportation, instead of keeping large trucks holding, natural gas, we can contain almost, I forget the exact, replica, like a propane tank itself. We can hold almost probably the same amount of gas in about, I think it's about 100 to 150 grams of our sample.
Wow,
Yeah.
that's pretty cool.
So because of the high,
Now Tom's interested, yeah.
What our gas tanks can hold at the volume, the differences in volume, we can maintain a large collection of gas. So,
So putting these materials into these frankens, then you're keeping the same mass, but somehow shrinking the
Volume.
Basically.
well, that's the one thing that we've left off, with all of the crystal structures, all these frameworks have an internal volume of nearly 6,000, kind of cubic angstroms. So with respect to molecular size, they can hold in a lot. And so technically, you're not shrinking much, it's just they're gonna fill up all that empty space. And they're gonna fit it, almost to a perfect, organization. So that's where the difference comes in within the crystalline aspects of it, is that everything fits perfect. And that's where we have that ability that we can hold large quantities of, say, gas molecules.
Okay, we're pretty much out of time. So if you do have any other questions for Charles or Dr. Hogan, I'm sure they would be happy to answer them later or over email or what have you. I would say very cool stuff. Thank you. I always love intercalation of molecules, and I only know about it from you talking about it at these colloquiums. So awesome. And thank you, Charles, for both doing the work and the presentation. And let's say thank you to both of them once again. Well done. And for those of you on Zoom, thank you for joining us. For those of you here in person, feel free to grab more food. Make sure that you have signed in, and so we know that you are here. And we'll have more on colloquium this semester, December 4th. I think it's also a Wednesday at 2 p.m. We'll be hosting our annual Dr. Newman virus lecture that I've told him he is on the hook for in perpetuity, and he just keeps agreeing. So he'll be joining us from College Station, where he's a chief virologist at the Global Health Complex, telling us something new and I am sure terrifying about viruses in our society. But yeah, it's going to be fun, I am sure. But anyway, all right. Thank you, folks. It's been good. There we go. Amen. Amen.